This is some of the pure mathematics topics. Now we're dealing with complex numbers. We start with the axioms given here. C, this donates to complex numbers, and its properties are: 1, closure for all Z1, Z2 contained in C, the complex number. Z1 plus Z2 is contained in within the complex number set. And associativity, Z1, Z2, Z3 are contained in C, so Z1 plus Z2 plus Z3 equals Z1 plus Z2 plus Z3, which is associativity within the complex numbers. Now, additive identity for all Z contained in the complex numbers, Z plus 0 equals Z equals 0 plus Z. Now we have additive inverses. For each Z contained in C, there exists a number, negative Z contained in C, such that Z plus negative Z equals 0 equals negative Z plus Z. Commutativity is our last axiom for addition. Now for all Z1 and Z2 contained in C, Z1 plus Z2 equals Z2 plus Z1. Now it's all straightforward. Multiplication, the axioms. We have closure for all Z1, Z2 contained in C. We have Z1 plus Z2 is contained in C. And associativity. For all Z1, Z2, Z3 contained in C, we have the same axioms as of associativity. Now, under multiplication, our identity has got to be 1, because we can't really multiply things by 0 to get any kind of quantity other than 0. So our identity for all X contained in C is Z multiplied by 1 equals Z equals 1 multiplied by Z. That's X, I shouldn't have really put that. But anyway, for inverses, for each Z contained in C minus the set 0, there exists a number of the inverse Z, which is contained in C, such that Z multiplied by inverse Z equals 1, and which equals the inverse multiplied by Z again. Awful, it's straightforward. Now commutativity. For all Z1, Z2 contained in C, Z1 multiplied by Z2 equals Z2 multiplied by Z1. So all straightforward. Now we're adding some of these axioms, combining addition and multiplication for distributivity. Now Z1, Z2 and Z3 are all contained in C. So Z1 multiplied by Z2 plus Z3 equals Z1 multiplied by Z2 plus Z1 multiplied by Z3. Now let's show this. We'll let Z equals X1 plus I Y1 and Z2 equals X2 plus I Y2. Let these both be complex numbers. Then the following operations can be applied. Addition, Z1 plus Z2 is this, subtraction is this, multiplication is this. It's all straightforward, easy to follow. Now we'll get onto the complex conjugate, Z with a little bar above it, of the complex number. X equals X plus IY is the complex number. And X minus IY is the conjugate of, no, this is the conjugate of a complex number, and this is a complex number. So the properties, let Z1, Z2 and Z be any complex numbers, then Z1 plus Z2 equals Z1 plus Z2, and 2 Z1 multiplied by Z2 equals Z1 multiplied by Z2 individually. Now Z multiplied by Z bar equals 2 REZ, where these represent the reals, which is a real of Z. Now number 4, Z minus Z hat, Z bar equals 2I imaginary. This represents the imaginary number of Z. Now the modulus, Z plus IY equal is the modulus of X plus IY equals this, the z, which is the square root of x squared plus y squared, which is standard geometry, school geometry, an example of which z equals 3 minus 4i, so the modulus is simply this, or 5. Now the properties. The magnitude of z has to be greater or equal to 0 for any z contained in C, with equality only when z equals 0. And 2, the modulus z1, z2 equals the modulus of z1 multiplied by the modulus of z2 for any z1 and z2 contained in C. Now, here we have an example of a distance formula, the modulus z1 minus z2, which is shown here. We have conjugate modulus properties here. I should have boxed this off separately. This is just a visual depiction, which you should all be familiar with, this school stuff. Now the conjugate modulus properties. The modulus of the conjugate equals modulus of the unconjugated, should I say, for all z containing C. Now the multiplication also applies here, the modulus squared for all z in C. And why this holds, I take z equals x plus iy, then z conjugate equals x minus iy equals x plus I minus y. So our magnitude is here, z, and that's why this property holds. Now the polar form, r equals the magnitude of z, which equals the square root of x squared plus y squared, and we can draw it on another little graph here. And this is how you show the special angles, which is always useful to know how these angles come about. Now for any theta contained in R, sine pi minus theta equals sine theta, and likewise all these are all just the basic identities that you're probably familiar with. Now again, expressing these in Cartesian, we have 3 cosine of pi over 3 plus I sine pi over 3, and cosine minus pi over 6 I sine minus pi over 6. Now first, for r equals 3, theta equals pi over 3, the required form is x, I, y. So putting these in the form, plugging in these values for x, we get 3 halves, and for y we get this. Hence, expressing this in our complex form in Cartesian is this. This is the answer. Now for r equals 1 and theta equals minus pi over 6, again we're plugging in these values and transforming, we get this in our complex plane, if you will, Cartesian, and noting that cosine theta equals x over r and sine theta equals y over r. And that's an introduction to this pure mathematics one for complex numbers. Please do like and subscribe.